Hi, welcome back. Today we'll start a new module, very exciting. It's cryptography. A little bit of math, but then still you don't have to have background, and it's all very easy to understand. Today we want to focus on symmetric key encryption. We'll also begin with Diffie-Hellman key exchange. And so just a little bit of recap on the terminologies. Last time we talked about file system integrity with a stronger threat model where you can have adversaries temper with the OS, the hash computation, the storage. In that case, how can you be secure and ensure your files integrity? And then we talk about the TPM and the remote server, BLP model, BIBA model, virus propagation, and just a little bit of a traditional OS security concept, race condition. We also talk about a more modern OS, Android security, and then it's permission-based system. Every app need to request for permissions. User need to approve at the runtime at least once. We also have our TA Solomon talk about code reuse attack, different flavors of it, and give you examples of control flow integrity in terms of how to ensure the indirect control flows where you have returns and making sure it's returned to the right place, as well as ASLR. Solomon's research has done a lot of interesting findings about how to make it more secure ASLR. For your project, if you're still picking topics, I want to share this. IBM has, of course, Watson can do all kinds of, play Jeopardy and so on. Watson was also used for cybersecurity in terms of gathering threat intelligence. And so read a little bit about it and think about how can you contribute from that perspective. Watson, of course, is not commercial, it's not freely available, but then think how can you use artificial intelligence. Essentially it's just machine learning and be able to understand and then sift through a large amount of documents, articles, news articles, and generate new insights. By the way, if you're looking for project partners, let me know. We still have students looking one student looking for a partner. Last time I was momentarily confused when I talk about BLP, and this figure ignore the indexes. This is the security level, the sensitivity level of object and subject. The indexes don't mean anything, and BLP is a confidentiality model. That means you can only write up, submit the information to your general, to top secret officials. But then the information won't, the writing will not allowed if it's downward. And so again, last time we talked about military general will not be able to email to a lower ranked official or an individual to ask him to buy some food. So this figure has no problem. And before we talked about cryptography, I want to say a little bit about password security. It's very important you don't store password in plain text, you hash it. Cryptographic one-way hash, that means you cannot, upon seeing the hash, be able to guess easily the pre-image, the original message, the original password. In addition, you also need to add a little bit of sort. It's a process called sorting. It's just random string, random number you concatenate and compute the hash. This way, if you have two people have the same password, then their hashed passwords will look different. Otherwise, you'll be able to say, oh, I somehow know Johnny's password, and Johnny's password hash value is the same as Alice's password hash, and therefore Alice must have the same password. So you want to make things different a little bit. The thoughts are stored in a database without encryption. You have to stop somewhere. And it just make it difficult for people to guess. And in particular, thoughts are extremely effective against the pre-computed hash attacks, which is a general form of what I just described, right? So suppose you don't know Johnny and you don't have this password, but then you can just guess, right? So you have seen Alice password hash and you're like, okay, maybe this is Apple. And then you compute Apple's hash and see whether it matches. And then it doesn't match, and then you say maybe this is orange. And so you can pre-compute all kinds of hash values, and you can share it with your hacker friends. And so make it very dangerous if you don't have thoughts. Then the information is relatively easy to break once you have this what people call rainbow tables. Thought make it more complex, and you have to guess the password and also the thought as well. And of course, this is assuming the database storing thoughts is not compromised. And so just to increase the brute force difficulties, make it harder for people. They cannot reuse pre-computed hash values. So symmetric key encryption, we of course have talked about this already. And the AES is a current standard. It stands for Advanced Encryption Standard. It became a standard in 2001, 19 years ago. And for when we talk about symmetric key encryption, we have sender and receiver all have the same key, K. The threat model is that the attacker may be eavesdropping, intercepting, tamper with the cipher attacks. Security goal, of course, is confidentiality. And then at the interface level, at the operational level, you have encryption, right? You have cipher attacks. You encrypt with a shared key, and then you obtain cipher attacks. And the receiver obtained the cipher attacks from the network channel, decrypted with the shared key K, and then obtains the message. So you're going to see a little bit of notation throughout our discussion of cryptography, and part of it is to make sure you're comfortable with it. Don't be intimidated by notations. We talked about Caesar cipher, which was used like 2,000 years ago for military communication. Is substitution cipher, and so pros is easy to remember, easy to read, easy to use. So of course, it's not very secure. And if suppose that you have this message, right? So suppose you have this cipher text. And people may be using some statistics in language frequency counting, right? Certain letter has high frequencies, and then when it's substituted, then this new letter has higher frequencies. And you know, in this case, you have a very, how many English words had this kind of pattern? Not very many, and then you know, it helps you break the message. This is the ciphertext. So, and you know, we talked about you don't have to just shift to the next third position. You can do all kinds of substitution, right? And you can compute the brute force complexity. Another way of doing cipher is called XOR cipher. This is relatively easy, and previously we talked about polymorphic virus encryption, virus being encrypted, and the metamorphic viruses. There's the XOR elements, right? You can easily just use XOR to XOR with the instructions. It's just bits. Because of the XOR property, the receiver just XOR with the same key and get the original plain text. And this has been used a lot in the history, called one-time pad. One-time pad is you have sender and receiver share hopefully a long secret key, and then you just do XOR with your message, and the receiver just do XOR and get the message back. And if your key, if your one-time pad is not repeating, hard to predict, completely random, then this is perfectly secure. And then people call it informatics secure. That means that you don't rely on any computational assumption. You don't have to assume, oh, I assume that this create log is hard to compute. There's no assumption. You just guess a lot of random bits. And if you can get it from the universe, you know, from anywhere, that would be nice. However, a lot of times that it's very hard to get those random bits, right? But if you get them, then this cipher is considered achieving perfect secrecy. What is perfect secrecy? Shannon, a very famous researcher who founded the information theory field and made seminal contributions to communications, define it thusly. You have a plain text, you have a guess with about the value of the plain text. Okay, and you guess is okay, I think the plain text is X, the message is X. And then your guess does not improve after you have seen the ciphertext of this encryption. Okay, so you have seen the ciphertext, which is Y. Okay, but the Y is so random, you don't gain any additional knowledge. And so the probability of your guessing before and after seeing the ciphertext is the same. And in that case, the ciphertext does not reveal any additional information, and we call it this happy encryption achieving perfect secrecy. And in reality, it's very hard to achieve this. This is an example one-time pad. Interestingly, you know, this is not as ancient as you thought. It will be. When I was in grad school, our department, before transitioning to public key system, we use one-time pad. Although it's not infinitely long. One-time pad is, I think is like 20 or like 25 numbers, and then they probably, you know, it was repeated, you know, just XOR. It was not extremely inconvenient if you travel and you have to make sure you print a big sheet of one-time pad, and then because every time you log in, you use it, and then that's gone, right? You have to use another one next time you log in. But then during one login, you just need one. And then we transition, the department transition to public key encryption, and you all generate keys and passphrases. So it's not extremely inconvenient, relatively secure, but you know, it's just not very practical. Symmetric encryption, our today's focus. So we want to spend a bit more time on DES, even though DES is considered not secure, don't use it, use AES. But DES has been around for a long time. It's relatively easy to understand. Before we start, I want to clarify two concepts very commonly used. The one is called stream cipher. The other is called block cipher. Stream cipher is where you have bits coming in and then you encrypt immediately, okay? And then block cipher is you sort of wait. You wait until you receive a blob of bits and then encrypt them together. It's called block. And so that is a block cipher. And in the cipher is just old-fashioned way of saying encryption algorithm. It has short keys, 64-bit keys, and only 56 bits are actually key bits, and 8 bits are computed from those 56. So it has shorter, smaller blocks. And it's a symmetric key encryption. That means the encryptor, the sender, and the receiver have the same key, and then they use the same key for encryption and decryption. The concept is a relatively simple substitution and permutation. and we explained the substitution and permutation before. We want to say a little bit more about specifically how this is done. The short answer is a table lookup. So there are rules about how would you substitute and permutate, and it's all encoded in a table. And then you will just look at the table and say, oh, here I have to substitute the row 1, column 2 with this value 3. Okay. Here is a high-level diagram of one cycle in DES. In DES has 16 cycles, and so each cycle has this operation. And right now it's a little bit hard to figure this out. First of all, I want to point to your attention, it split the block in half, 32-bit left half and 32-bit right half. And then you see the right half, you don't do anything at all. The right half just directly go to the next cycle at the left half. Okay, so that's easy. Okay, and then here is a mathematical notation. In round j minus 1, the right half is the same as the next round j left half. Okay. Well, and then the left half there is an XOR operation here, okay, with a whole bunch of things happening here. So, and we'll explain the substitution and permutation box, how it's done. And then in the meantime, where is the key? The key is going into the substitution box, okay. The key is going into the substitution box. And then you notice that the substitution, before you're going in, things will be expanded to 48 bits. You see this right half is 32 bits, but then at some point there's an expansion of this to 48. So and you may ask, okay, is there any reason why it's done this way? Well, no, it's just the empirical. People like back in the 70s, they decided this is the best practice, best effort they can come up with. And it worked out well for a while. And then with the more computation power, this becomes insecure. So as I said, DES has 16 cycles. What you just saw was one cycle. Here's more cycles, and you see the left and the right keep interleaving. The information come into the different the next cycles. And so before we go into S box and P box and substitution box and permutation box, I just want to explain the expansion and then the reduction of bits. And you can do that very easily. And sometimes you just omit some bits like here, and then you have reduced bits, the reduced output. And then sometimes you duplicate one bit gets copied in 2 places, and then you can expand the number of bits. And so it's entirely up to you. So next I want to explain a little bit about the details of one cycle in DES. And I want to say that having a little bit more knowledge about DES would help you gain better intuition about symmetric key encryption. Even though this is not used, a lot of the concept still exists in AES. Permutation is a lookup table. It's very fast, and so DES can be implemented extremely fast, a lot of hardware support as well. And so here is just say if the original bit 1 will be copied into 2 places, one is bit 2 and then the other is bit 48. Right? So you see there is expansion going on. There's also permutation, right? Permutation means you change the position of places. Similarly, if you say, okay, bit, the original at a bit position 19 now goes to bit position 28. And so this is how you read the table. The original last bit, and now it gets copied into 2 places, 47 and first. So this is permutation. Substitution is more complicated. substitution is, I would also say, very important in terms of creating confusion in the ciphertext. And so okay, this is just another permutation box. When you go to different positions, this is the lookup table for the substitution box, S box. When you say S box, it refers to this in the DES. And so you again, table lookup, you have some rows. Okay, you have rows and columns, and so sounds like, okay, if you identify row and column, specific row and column, and then a specific S, you'll be able to read a number. Okay, what does that mean? So we have 6 S boxes. We have 8 S boxes, 8 S boxes. Okay, and so here are some more S boxes. How do we use it? How do we use it? Before input goes into the substitution box, it's divided into 8 blocks. And so because of expansion, you obtain the original input is 48 bits. And divided by into 8 blocks, that means 6 bits per block. And so you just figure out how to rearrange those 6 bits within a block, and then do this block after block. Okay, and all you do is just read up the certain bit positions and then use them as coordinates in the S box to point to you a new value referred to this coordinates, and then the new value will be the substituting value. Okay, so you use all the value as coordinates to look at a position in the lookup box. And so suppose we are talking about block 7, right? So we have 8 blocks, and we have already done 6, and we are now in the block 7. Block 7 has bits 0, 1, 0, 0, 1, 1. And what you do is you take the first bit and the last bit and then put them together as if it's one value. In this case, it's 0, 1, so that's 1. And then the rest of the bits form another number, and in this case is 1, 0, 1. In binary form, that is 9 in decimal points. And now you are in business because you can, according to the definition of S box lookup, that means it's pointing to row 1 and column 9. Okay, and then the row and the column start with 0. So then you look at, okay, because we're talking about block 7, so we look at the previous big table, we look at S7, the S7 box. And so you start 0 row, first row, that's what our row, and then you look at the 0 column, first column, second column, blah, 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 until you find the 9th column, and it's pointing to 3. And then you're done. You just substitute the B7 block with 3. And it's important to know that the result is 32 bits. You're reducing the bits, and so this is intended, because you have to do XOR afterwards with the left side. So that's just how you use the S box, the lookup and the permutation, and then you do this following this procedure. This is, if you look at the upper right corner, you have the substitution, permutation, and then you are going to have the new right half. The new right half is used in the next cycle, and you do this for 16 cycles. Here are some notation that specify how the encryption is done. And so, of course, here it says function of the previous cycle's right half and the key, and then you know that there's a lot of operations in that function. And decryption, you can rewrite above symbolizing how you decrypt. When you decrypt, the operation is exactly the same, and then you just decrypt backward. Okay, and so you have the last cycle, and then you decrypt the 15th cycle, 14th cycle, and eventually you obtain the original plain text. And you can verify that you give the same thing. So we're still, so that's basically how DES work. You have, again, you split, for each block you split into half, and then for one half you do a lot more work, the other half you do less work, and then you get the new left half and right half, and it goes into the next cycle, do this again. In the meantime, there's keys coming in and into the operation. So the key information is incorporated in the encryption, but you're not done, because it's very important. There's a concept called Cipher Block Chaining, CBC. And before we show this penguin picture, this gray image of penguin is user electronic cookbook mode, which is not secure, because each block is encrypted separately, independently. What we want is chaining the blocks, and so that everything is diffused, making the ciphertext completely as random as possible, independent from the ciphertext. And that is your goal. Your goal is that there's absolutely no correlation between ciphertext and the original message. And of course, if you have the right key, you can decrypt. And so you see the paradoxical aspect of it. It's harder, right? On one hand, you can be decrypted if you know the secret key. On the other hand, if you don't have the key, it's just completely random looking. And so here's the illustration of how you do the cipher block chaining. After you've done one block, the ciphertext will goes in as the initial vector to the second block. And so there's this concept called the initialization vector, which is used when you do array block. And then the blocks gets chained through this this input. So each block's output is the input to the next block. It's partly the input to the next block, right? So you have the next block's plain text, but then you also has the ciphertext from the previous block. And it's extremely important for this because you want to disrupt the deterministic aspect of the encryption, meaning that same ciphertext, same plain text need to produce a different ciphertext. And if you do block by block, you will run into this very deterministic encryption, because a lot of protocols, they use the same word. They begin with HTTP, blah, 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 you know, www, blah, blah, blah. Then it's very predictable what the plain text is. And when the attackers see both the plain text and the ciphertext, they will be able to guess the key, and then be able to use that to guess the key to decrypt the whole thing. And we have seen this being the main vulnerability for many encryption algorithms, including WEP, which used to be the standard for Wi-Fi communication, though access point protocol and no longer it is. As well as if you watch the imitation game when it describes Alan Turing breaking the Enigma code, that they also leverage this aspect in the Nazi Germany's encryption algorithm. So and now including the midway, right? So we talk about midway or the AF, right? So determinism is bad for encryption. So you want to have, this is another illustration of how you do cipher block chaining. You give it the initial vector, and then the initial vector is sent over to the sender with no encryption, because sender needed to bootstrap the process, right? So they needed to get things started. And then afterwards, the cipher text become the initial vector for the second block, and so you chain everything together. But however, even DES with cipher block chaining is not secure enough for today's internet, and so don't use DES. Okay, don't use DES at all. Use AES. AES is a new standard. I mean, when you say new, it became standard in 2001, 19 years ago. Besides permutation and substitution concept, those traditional symmetric key concepts and techniques, it also involves some computational assumptions, computational operations. We'll not go into details of this. Extremely, substantially more difficult to break. So back in 2001, NIST, the National Institute of Standard and Technology, estimates it take 149 trillion years to break AES, assuming if you can break DES in 1 second. So it's a hugely more difficult to break. So two Belgian cryptographers invented AES. Okay, and that was a competition, I think. Keys are longer, and you get the different options for key lengths, and also it's actually quite fast. AES is considered fast. So you don't like you say you will never say, oh, we don't want to use AES because it's too slow. No, AES is extremely fast, and also the computation power is a lot more fast. It's just faster and faster for phones and for devices. Before AES, people also use some like makeshift algorithm based on DES. It's called 3-DES or triple DES because DES has very short keys, and they said, okay, maybe we should use it 3 times, and so that will give us 3 fold of security guarantees. And there's just a different way of using the keys. You can have same key, 3 different keys, and then so on. And so in general, people NIST recommend AES, not 3-DES. So don't use 3-DES. But this has been used in practice for a while as just a mitigation. A very important question is, how do you know some symmetric key encryption algorithm is secure? And this, of course, is a challenging question. There's no easy answers. You don't know because there's no proof. A lot of the substitution and permutation are, what is it called, the information theoretic secure, in the sense that you have enough random information that make it extremely difficult for attackers to decrypt. And so a lot of the analysis, even if there are, it's based on empirical, sort of based on experiences, analysis, not on formal proofs. There's no formal proofs showing that certain like AES is secure. For example, DES, and one approach called the differential cryptanalysis. The differential part is that you look at, is this cipher output more frequent than the others, does that indicate that the plain text or the key has a certain bias? In general, we want it to be completely random, no correlation, right? The ciphertext and the plain text. But then if there is some correlation, then people will be able to find it out. For example, a typical S box, you have this type of input and then plus key, and then you do the output. What we have just shown, right? The block 7, and then you get certain value. However, people may find that, and this was people discovered the actual research results. If the plain text D means differ, S means same. If two plain texts have certain type of patterns, then their ciphertext would also exhibit certain patterns in a way that are not evenly distributed. And so certain certain patterns in the cipher in the resulting ciphertext will have much more frequent, right? Much more frequent than the ideal case. Ideal case, you want to have all the different configurations to be the same. And so of course, this does not directly translate to certain key value or message value, but then you just gain more information, which in general is not good. Recall that we look at the Shannon's perfect secrecy definition is that you don't gain any information, but sometimes you do, and that's not good. Another type of issues typically involved is called side channel attacks related to the implementation of the algorithm, not the theoretical design, but the actual coding of it and execution of it. Attackers may observe power consumption, timing, cache, and certain ways to infer the certain bit value of the key. Maybe certain key bits take more time, more power. And so Patrick Chaumont is a professor at WPI Worcester Polytech, Polytechnic Institute, and then formerly at BTECE. He has done a lot of work. So look it up if you're looking for a class project. Side channel attacks has been extremely difficult to detect, and a lot of the preventions are just doing some additional operations so that, say, you making sure that the array bits will spend the same amount of power, same amount of time. Symmetric key encryption, the biggest disadvantage, of course, is that you have to have the shared key. And so back in the 70s, and this is a long, long time ago, 1976, and Diffie-Hellman, two-person invented what is called the Diffie-Hellman public key exchange protocol. And this was the first public key encryption algorithm prior to RSA. And this is also relatively straightforward. So we'll explain before we end this today's class. This is a completely different beast. Okay, completely different beast from symmetric key encryption. Before we have this substitution, permutation, and here is real number theories, computational hardness assumptions, and the specific hardness assumption is a discrete log problem. We assume is difficult, meaning that people cannot guess the exponent. If you know the value and then the base, and you just don't know the exponent. In this particular setting, specifically given integer n, and then a base, G, the generator, and then the prime number P, the exponent K, where you have G to the K and modular P, modular operation is a very common operation in cryptography, and for now you can just consider modulo as not being there, and so you just everything essentially you do modulo, and so guessing the value K when you know N and G and P is extremely difficult, and this is assumption. In reality, you may wonder, okay, I compute like square root of 4, square root of 9, 16, 81 all the time, right? So, but then, you know, that's when the values are very small. The N is very small, and but then when this value is big, and then you have modular operation with a prime P, this is difficult. And so you know, the computational difficulty is just a number theory fact, but that fact cannot be used to build an actual protocol that people can use to communicate. And so that's the important difference between CS and the math, is that you utilize those mathematical facts and put them together and make it a protocol so that people can actually use. And so today we want to say a little bit more about the actual protocol. The protocol is relatively easy to understand. I want to just go switch to stop sharing here. Okay, you should now see a whiteboard, and we have done this before, so you have a G, right? This is, you know, we call it a generator, and it cannot be, you know, 0, 1, or P minus 1, so we said it cannot be 1. It's just, you know, all these degenerate cases make it easy to guess. And then you have a large prime P, okay. And then you have Alice, Bob. So what they do, each of them would do is pick a secret. Pick a secret and then call it the private key K Alice. Okay, and so let's just give it as A. And similar B. And you know, it has to be a big number. And then they compute their own public key. In this case, is the way it's defined is you raise to the power, you raise the G to the power of SA, and in this case, Bob is okay. And now they each have a private key, which they keep it secret, and then they have a public key. Public key, of course, they can send to each other. So, and that's what they do. So the next step is they have each other's public keys. The next step is the most important step in Diffie-Hellman key exchange protocol. Key exchange protocol is to raise the public key of Bob's to the power of SA, that is a secret key of, and then, you know, we call it key shared. This is a shared key, okay? And similarly, Bob does is raise Alice public key to the power of SB and then mod P. And then this is Bob's shared key. And then they use the key shared to communicate, okay? So like encrypt a message, use a key shared. They of course can use the public key to encrypt, but it's gonna be slow, okay? And so they want to establish a shared key and use a shared key too. And you may ask, okay, once they establish a shared key, what specific algorithm? Then they can use AES. Right? AES has a it needs a key, right? AES needs a key, and then this key shared can be used as AES key. So you sort of do the public key exchange and then use transition to symmetric encryption. And that's what the internet, everybody does in internet. Of course, they use RSA to establish the initial shared key, but then it's very important you use shared key and AES in the subsequent communication because that's a lot faster. So that's a protocol. It's relatively easy, and then you may wonder, okay, what's the magic here? How come they each do their own computation and then they get the same shared key? Well, so then let's just verify, right? So in Alice's case, pub k b s a mod p, what is it? Well, pub kb is G to the SB, right? Is this. And we can do mod B mod P altogether later. And so it's essentially this. And of course, this is GSB SA mod P. And you can, and so this is Alice on the Alice side. For Bob, you can do the same thing. What is pub KA? Pub KA is this. Right, so it's the same thing, same key. Okay, so that's it. And so you should also go back and then make sure that you confirm this yourself, and this is I want to say this is something that I would like you to remember because it's relatively easy to understand, and so something to remember. We'll come back to it next time when we talk about the security of it. It's very important to understand that there's a very, very serious issue, security issue, and see here some numbers that you can play with to confirm that you do get the same key. Man-in-the-middle vulnerability, because there's no way that you know that you are talking to Alice, and so it's the same man-in-the-middle issue, right? So we talked about man-in-the-middle so many times, and this is exactly have that problem. How can you know that you're actually talking to Alice or Bob? You just see some numbers. So next time we'll explain this, and then we'll talk about RSA. That's it for today. We'll resume our crypto discussion later this week. Thank you.